Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome, everyone. Today, we are initiating the control protocol. This is not just a theoretical framework. It is the fundamental operating mandate for building reliable, trustworthy, and actionable intelligence systems. We are moving beyond simply interacting with large language models. We are moving toward engineering truth in the generation core. In the current landscape of artificial intelligence, the ability to generate information is common, but the ability to generate verifiable truth is the ultimate challenge and the highest priority for mission-critical systems. This protocol details the stringent architecture required to domesticate the immense power of generative AI, ensuring that every output adheres strictly to our operational and ethical standards. This requires precision, discipline, and a strict set of non-negotiable rules governing the system's behavior. Over the next few minutes, this presentation will walk you through the three core directives that govern the machine's reality, the architectural choices we must make to maintain data sovereignty, and the adaptive strategies required to efficiently fuel the core without causing systemic collapse. Get ready to dive deep into the architecture of control. Let us first define the entity we are working to control, the generation core. We have successfully retrieved the raw intelligence. We now possess the key to interface directly with the generator itself, which is a vast, multi-dimensional, latent space entity. Think of it as a limitless, chaotic ocean of data and potential correlations that hold enormous predictive power. Its power is immense, bordering on the mythological in its scale and speed. But critically, its raw, default behavior remains fundamentally unaligned with our specific mission requirements for truth and accuracy. Leaving its behavior unchecked results inevitably in speculation, hallucination, and inconsistencies. We cannot afford output errors in our deployment environment. Therefore, the core mandate of the control protocol is crystal clear. Our task is not merely to ask the system questions and hope for the best, but rather to command the system with absolute authority. We must impose structure and accountability onto this latent space, enforcing rules that bind its generation process, turning a chaotic force into a reliable, verifiable instrument of truth. To ensure operational integrity and to enforce our command structure over the generator, every single query, every single command, is bound by the architect's mandate. This mandate consists of three core directives that are permanently embedded in the foundational system prompt. Crucially, these are not mere suggestions, nor are they helpful guidelines to follow if convenient. They are the immutable laws of the machine's reality. If the machine cannot comply with these directives, it must immediately halt the generation process. The first directive is truth. This mandates absolute source grounding, ensuring the output is derived solely and exclusively from the provided documents. The system must not speculate or utilize outside knowledge. The second directive is adherence. This enforces rigorous citation, demanding verifiable links back to the original source data for every single factual assertion made. Accountability must be baked directly into the output. The third and final directive is reasoning. This requires the model to engage in a formal, observable chain of thought process, systematically verifying its internal logic and checking its adherence to the first two directives before executing the final output. Together, these three directives transform the raw generation core from an opaque black box into a transparent, auditable, and reliable instrument of truth. This layer of control is non-negotiable and provides the foundation upon which all subsequent architecture is built. Let us take a directive deep dive to understand how these laws are technically enforced and what mechanisms are required within the pipeline. Directive 1, truth or source grounding, means the core must only use the provided context streams. This is an explicit instruction to ignore all external knowledge contained within its massive training dataset that is not explicitly in the context provided. If a fact cannot be sourced directly from the input prompt, it must be discarded. Directive 2, Adherence, requires strict citation and traceability. As the diagram illustrates, for every generated factual assertion, such as assertion X is true, the system must immediately link that assertion to its specific source data block, denoted here as SRC001. This ensures full traceability and eliminates plausible deniability regarding the origin of information. Directive 3, Reasoning, activates an internal diagnostic, running a chain of thought, or COTI, before execution. The system performs a self-verification step, checking its own logic flow and adherence to the first two directives before generating the final verified output. This internal check prevents logical leaps. Now, the ultimate safety mechanism, the final failsafe. If, during the COTI process or final output generation, compliance with all three directives is deemed impossible or compromised, the system must immediately halt and respond with the sole, unambiguous output: unknown. This absolute failsafe prevents the system from generating speculative, ungrounded, or potentially harmful responses under any circumstance. The effectiveness of our control protocols, the three directives we just discussed, is entirely dependent on the nature of the generation core itself. We now move from mandate definition to physical mechanism. This leads us to the primary and most critical architectural decision: choosing the engine. Do we integrate a proprietary black box core via an external API, or do we forge a truly sovereign core in-house, hosted entirely within our own secure perimeter? This decision is inherently a high-stakes trade-off between immediate convenience and long-term control. Think of it like choosing the delivery vehicle for highly sensitive cargo. You simply do not use a heavy semi-truck to deliver a single, critical, secret letter, as the risk and overhead are too high. If the cargo, our data, is highly sensitive, we need a secure, low-profile vehicle designed specifically for high security, low external transport risk. The choice dictates our ability to enforce compliance, fine-tune performance, and most importantly, maintain absolute data sovereignty. The prompt interface, where our commands and context enter, must be linked to an engine we can trust implicitly to follow the protocol. We must meticulously analyze the specific mission complexity and data sensitivity before committing to either the API route or the self-hosted sovereign route. This foundational choice determines the long-term reliability, security, and compliance of the entire system. Option A represents rented intelligence, the proprietary core accessed via API. The operational method is straightforward. A secure API call is made from our local network to a major external provider like OpenAI, Anthropic, or Google. This architecture involves sending the context and the prompt from our secure local network out to the cloud intelligence, which then performs the generation and returns a response. The key strength of this approach is undeniable and compelling: unmatched reasoning and synthesis capabilities. These proprietary models are often the state of the art, essential for tasks that require highly complex logical acrobatics, such as comparing conflicting clauses across multiple legal contracts, financial models, or synthesizing massive external datasets into novel insights. However, the primary constraint is severe and often mission-critical: data sovereignty. Every piece of context, every sensitive document required for the task, must be transmitted offsite to a third-party provider. For organizations dealing with highly regulated or sensitive financial, health, or governmental data, this represents an unacceptable compliance risk and is frequently a non-starter from a legal standpoint. The security perimeter extends far beyond our direct control, compromising the integrity of our data stream. Option B represents owned intelligence, the sovereign core, which is entirely self-hosted. In this configuration, the generation core operates through local inference running on dedicated specialized hardware, such as on-premises servers equipped with high-performance dedicated GPUs, like the NVIDIA H100. Critically, context and data packets never leave the secure local network. The key strength here is absolute and total control, coupled with ironclad data privacy. The core operates completely within your secure perimeter. This means the system can be fine-tuned extensively on highly sensitive internal datasets and even run completely air-gapped, meaning it is disconnected from the external internet, meeting the highest levels of military or governmental compliance. However, This level of control comes with a steep primary constraint: significant infrastructure overhead. Running large, state-of-the-art open-source models requires enormous upfront capital expenditure for compute resources and specialized, ongoing engineering expertise to manage the inference stack. It is a critical misconception to believe that free model weights translates to free to run. The operational costs, including cooling, power consumption, and maintenance of dedicated GPU clusters, must be rigorously factored into the total cost of ownership. Since there is no single best core for all missions, we utilize the selection matrix to guide our architectural decision. The choice is fundamentally a function of two critical variables: mission complexity, mapped onto the x-axis as reasoning complexity, and data sensitivity, mapped onto the y-axis as data privacy and sovereignty. Our primary objective is always to balance state-of-the-art reasoning capabilities against the absolute necessity for sovereign control. Looking at the bottom left quadrant, we find low complexity and low sensitivity, where models like GPT-4o Mini or Haiku provide fast, cost-effective API access for common tasks where data leakage is not a concern. In the top left, we require high data privacy, but only moderate reasoning complexity. Here, a self-hosted Llama 8B is the perfect fit, keeping the data secure while efficiently handling straightforward tasks like document retrieval and simple summarization. The bottom right is reserved for highly complex tasks involving large-scale, but non-sensitive public data, where the raw power of external API models like GPT-4 or Claude 3.5 Sonnet is warranted. Finally, the top right quadrant represents the most demanding missions: high complexity coupled with high data sensitivity. This scenario necessitates large, robust, self-hosted models like Llama 70B or Mistral Large, absorbing the infrastructure overhead to achieve both state-of-the-art reasoning and full data sovereignty. The matrix ensures the core engine is always optimally matched to the mission profile, never overcomplicating security for a simple task and never sacrificing security for a complex one. Having chosen and architected the generation core, we now turn our attention to the fuel that powers it: context management. This is where most initial, unrefined deployments fail and where efficiency collapses. A common and catastrophic operational error is the naive assumption that we should simply overload the core's active memory, known as the context window, with every piece of potentially relevant data. The assumption that more data is always better is a critical fallacy in modern generative AI operations. The core, despite its immense size and processing power, is still subject to computational and cognitive limits. Dumping excessive, irrelevant, or redundant context creates operational noise, drastically increases latency, and fundamentally degrades generation performance. Overloading the context window leads directly to three critical system failures that compromise the entire control protocol, fundamentally violating the spirit of the truth directive. We must move past the fire hose approach to context input and embrace surgical precision in context delivery. Understanding and mitigating these three failures is crucial for maintaining the integrity established by the three core mandates. System failure 1 is the critical, lost in the middle anomaly. This chart clearly illustrates the cognitive limitation inherent in even the most advanced generation cores. As the context length in tokens increases along the x-axis, we see the accuracy of the model rise rapidly as it gains necessary information, hitting an optimal focus zone, typically positioned around the 4,000 to 8,000 token mark, depending on the model. However, beyond this optimum, as cognitive load increases, the core's focus begins to degrade catastrophically. The critical signals that the model needs to retrieve and act upon, such as the specific answer to a question, get buried and obscured in the noise of surrounding, less relevant context. The model literally gets distracted or overwhelmed by the sheer volume. The system knows the answer is somewhere in the input, but it struggles increasingly to locate and cite the specific piece of data required for compliance with the truth and adherence directives. This results in a sharp, undeniable drop in accuracy, illustrated on the y-axis, and a corresponding spike in ungrounded assertions. To maintain the integrity of the control protocol, we must ensure our context streams never venture into this long tail of diminishing returns, prioritizing absolute quality and relevance over sheer volume. System failure 2 addresses the practical and economic constraints of latency and cost overload. It is a simple, unavoidable truth of AI operations. Every single token of context consumes time, specifically time to first token, or TTFT, and energy, which translates directly to compute cost. As shown by the red line, the cost per query increases exponentially as the context size grows. Compare this cost increase to the accuracy, shown by the blue line, which plateaus rapidly and then begins to decrease due to the lost in the middle effect. Beyond a certain point, the marginal gain in accuracy is negligible or even negative, yet the cost continues to skyrocket with every additional token. This clear divergence defines the critical Goldilocks zone. We must operate where we achieve near maximal accuracy without incurring the exponential penalties of oversized context windows. If we send 50,000 tokens when 5,000 highly relevant tokens would suffice, we are essentially paying 5 to 10 times the cost, delaying the response time, and, critically, paying a premium for noise. Efficient fueling is therefore not just an architectural nicety. It is an economic necessity for any scalable, high-throughput operation. Given the severe risks associated with context overload, we cannot use a fixed, maximum cognitive load for every query regardless of mission type. The solution lies in implementing adaptive fueling protocols. We must adapt our context delivery based entirely on mission parameters, using intelligent routing protocols to provide only the minimum viable context required for the specific task at hand. The process starts with the input query, which is categorized either as a simple fact query, perhaps requiring retrieval of a single number or date, or as a complex synthesis task, requiring comparison and structural output from multiple sources. This query is routed through an intelligent routing module. The module uses a fast, lightweight classifier to determine the appropriate context payload size. A simple fact query may receive only one small, highly relevant chunk of context, while a complex synthesis task receives a larger, distilled set of documents. This dynamic approach ensures that the core is never underfed, having exactly what it needs, but crucially, it is never overfed. This simultaneously mitigates both the lost in the middle anomaly and the latency and cost overload failure modes. Adaptive fueling is the linchpin of efficiency and resource management in the control protocol. To successfully execute adaptive fueling, we deploy several core context optimization strategies that manage the flow of data into the core. Strategy A is the foundational hard cap, or token budget. This is the simplest and most effective initial method of risk mitigation. We set a fixed, safe token budget, for example, 4,000 tokens, which we know operates within our tested optimal focus zone. We then fill this budget with only the top-ranked, most semantically relevant document chunks based on similarity to the query, and then we strictly stop. This is simple, effective, and directly prevents system failure 1. Strategy B is the dynamic accordion window. This is a more sophisticated method, utilizing a classifier within the routing module to automatically assess the complexity of the query before context is provided. If the query is simple, the context window remains small, like a closed accordion, minimizing latency. If the query is demanding, requiring deep synthesis, the window expands dynamically to accommodate the necessary context, maximizing relevance while still maintaining a hard ceiling to prevent catastrophic overload. Strategy C, information distillation, addresses the challenge of documents that are inherently too large for even the expanded window. For these, we first use a smaller, faster, less expensive model to pre-process the document. This model's sole job is to summarize the massive document into key, high-density bullet points or facts, which are then fed as context to the primary reasoning core. This distillation maintains the critical signal-to-noise ratio while significantly reducing the token count, ensuring that only the essence of truth reaches the generation core. We now arrive at the final stage of system integration, the complete protocol. A successful generation pipeline is not, as many believe, merely a chaotic firehose of data fed into a large model. It is a precise, surgical instrument governed by strict architecture. The entire process is a synthesis of three core operational elements that work in lockstep. First, we have precise command, which is defined by the directives. The prompt interface injects the user's query along with the immutable laws of the system prompt, ensuring the core knows its boundaries and mandates before processing any tokens. Second, there is strategic core selection, the engine itself. Based on our selection matrix analysis, we ensure that the generation core is the optimal size and residency for the mission's complexity and data sensitivity, leveraging either a sovereign or proprietary model. Third, and critically, is efficient fueling. The routing module activates the adaptive context protocols, applying strategies like distillation and dynamic windowing to provide the minimum viable context required. This minimizes cost and latency while maximizing accuracy. The integrated result flows into the generation core, which performs its internal chain of thought diagnostic, verifies its logic, and adheres strictly to the citation requirement. The final output is the ultimate goal, a verified and cited response, compliant with truth, adherence, and reasoning. This complete architecture transforms potential chaos into operational certainty and auditable truth. We conclude with the core philosophical and operational takeaway of this entire presentation. When dealing with the immense, unaligned power of the generation core, we must remember this truth. Control is not a feature you bolt on later. It is not an afterthought, a patch, or an optional setting you toggle in a configuration panel. Control must be baked into the fundamental structure. It is the entire architecture. From the system prompt that defines the machine's reality and the mandates of truth, to the routing module that dynamically manages its cognitive load, to the choice of the sovereign hardware itself, every single component must be designed and implemented for maximum accountability and verifiability. This protocol is designed to ensure that the answers we receive are not just plausible or fluent, but they are provably true and traceable back to the source data. Building reliable artificial intelligence for high-stakes environments is hard work, but by imposing the three directives and implementing adaptive fueling, we successfully move beyond mere intelligence and into the critical realm of engineered truth. Thank you for attending this briefing on the control protocol.